Hello everyone, this is Nikita. Welcome to the episode 65 of Microsoft Hour of Code brought to you by Millionlights. Millionlights is a TV channel dedicated to improving skills of people and their employability. Now, let me tell you more about Microsoft Hour of Code. Microsoft Hour of Code is a series of lectures, courses and talks by experts who are going to discuss the latest Microsoft technologies, topics related to programming and industry forecasts that are all focused on employability. We are learning developing Microsoft SQL Server Databases. This course is basically for people pursuing computer science. This content has been created by our partner Microsoft, and today we have Malcom and Bolton from Microsoft with us. Our experts will take you through tables, indexes, stores procedures, and other database objects. Learn about techniques from designing indexes, managing transactions, and optimizing performance and concurrency, and get best tips and practices. These courses can help you earn at least 4 lakhs a year, and for those who are already working, experience strongly influences pay in this job. So you can definitely get an increment in your salary. Now, let's move on towards the courses. Developing Microsoft SQL Server Databases. The topic we covered in the previous episodes are implementing tables and views, implementing indexes, and implementing stored procedures and functions, managing transactions, implementing in-memory objects. In this episode, we will cover the remaining part of implementing in-memory objects and optimizing and troubleshooting queries. So let's get started with implementing in-memory objects.
Should we have a look?
Yeah, let's take a look.
Okay, so I'm going to use the AdventureWorks Data Warehouse database for this one. I'm going to execute this query, a couple of joins, just to get it into cache. Now I'm going to set statistics time on and statistics IO on because we want to compare and contrast the execution times for this. And I'm going to run this query. Take a measure on the messages here. So what we're looking for here is this. So we've got a CPU time of 1766 and a elapsed time of 909 milliseconds.
Okay.
So let's take these stats off. We're going to create a non-clustered column store index. A second to create. So we try and insert a row here, which will fail. Why will it fail?
It'll fail because it's a non-clustered column store index, so the table's read-only.
So it's read-only. So we can't update a table with a non-clustered column store index. But we can read from it. So let's set these statistics back on and see if we can spot an improvement here. So we've now gone down to 483 of CPU time. So that was 1766. So what's that? A third?
Yeah, that's a significant improvement.
Before.
And if you think, the larger that table would be, the more dramatic the improvement would seem. It was pretty quick to begin with because it's just sample data, but if you had a query that took several minutes to run, cutting that by a third is actually a fairly significant gain.
Yeah, or 2/3 in fact.
Yeah, indeed, yeah.
So let's switch those timings off again, and let's drop that index. And we'll create a clustered column store index, so that's going to affect all of the columns. Notice now that we can insert the rows that failed
so the
previously.
table's updatable, like a regular table.
I'll switch that on. Hopefully. So, and again,
it's there or thereabouts. It's just a little slower in this instance, but other factors would affect that. it should be comparable to the
But
non-clustering.
from the original query, it's still more than 2/3 faster, which is quite significant. It's quite a significant gain.
I guess just before we switch away from the demo, one thing I do want to sort of add to all of this, we've talked about the fact that a clustered index is updatable when a non-clustered, other than using various techniques, makes the table non-updatable. Just want to kind of explain a little bit of how that works under the covers, because when you use a non-clustered column store index, one technique that's quite often used is you have your table, which contains your data, but you may create something that goes along with that table, another table that has the same structure, which you use as a kind of temporary writable space. And when you query your table that contains the non-clustered column store index, you union the results with this, let's call it a delta table, which contains the changes, and then periodically you merge those in. So there's a technique where you can implement some logic to effectively combine two tables into one logical view of the data and then periodically merge the changes in. And actually, under the covers, that's how a clustered column store index works. Internally, SQL Server maintains a traditional row-based delta table portion of that table plus the column store in memory part. So when you do an insert or an update, what actually happens is that delta store table is modified, it's stored on disk until we reach a threshold where a certain number of pages have been updated, and at that point under the covers, SQL Server will take those and absorb them into the column store area. So there's a certain amount of additional complexity under the covers when you use these things that you might not immediately be aware of. And there are dynamic management views you can use to see, well, what's currently in the delta store versus what's been absorbed into the table itself. But it's worth being aware of that.
Yeah, excellent.
Okay, let's switch back to the slides. And moving on from there, let's look at, I guess, what most people will think of as the in-memory feature for 2014. This was the big headline additional new capability in SQL Server. The code name was Hackathon. For a while, we had lots of people talking about Hackathon. So if you do hear that word, it refers to this technology that we're going to talk about now. So Christian, take it away.
Thanks, Graeme. So InMemory OLTP, as Graeme said, is the brand new feature for SQL Server 2014. The code name for it was Hackathon, and it's still kind of referred to as Hackathon. It's a bit easier to say than InMemory OLTP. But certainly for the purposes of the product feature in the exam, it will be InMemory OLTP. So it's essentially a high-performance OLTP feature. So online transaction processing is the target scenario for this, and it consists of two parts: memory-optimized tables and natively compiled store procedures, which are used to access memory-optimized tables.
Okay, so let's deal with the first of those two things, and let's look at memory-optimized tables.
So let's have a talk about what are memory-optimized tables. So what's quite interesting in the fact that this in-memory feature for SQL Server was really designed with two parts in mind. It had to be part of the product itself, not an add-on product, and it needed to be integrated. So you didn't have to have an in-memory database. You could take the parts that were relevant to you and put them up in memory. And the first thing is a memory optimized table. So when you make a table memory optimized, SQL Server will actually take that definition as a C structure and compile it into DLLs and load it into memory. So every time you then insert into that table, what's happening under the covers is that SQL Server will be using DLLs to interface with that table, because it's not a normal table structure anymore.
So it's actually it's converted. Your transact SQL that you use to create the table is converted to C, which is then compiled to a DLL, and that DLL is loaded. That's what's in memory, that
Exactly,
DLL.
exactly. So it's very, very high performance and very efficient. So we don't have any locking semantics on in-memory tables. So we don't have any locking and blocking problems. So everything will run using snapshot-based isolation levels. We can index using hash indexes. Okay. It can coexist with disk-based tables, and this is really the key thing for integrating this technology into existing applications. As I mentioned before, you don't need to have this separate database, this separate application that you're rewriting. It can coexist with disk-based tables, and you can also query a memory-optimized table using T-SQL as well.
Oh, right, so I don't have to write any different code. I get query it just like an ordinary table using a Translate SQL.
Yeah,
statement.
exactly.
Oh,
exactly.
okay, great.
So scenarios for memory optimized tables. So the real key scenario where you get the most benefit from this is where really kind of high concurrency scenarios where you've reached the scalability limitations for the traditional architecture around SQL Server. And this is this limitation around locking and latching. So regardless of how fast your memory is or your disk is, we're still bound by this fundamental structure of latching pages in memory and the blocking that's associated with those. So without those latching mechanisms, the throughput that you can get and the scalability is much greater when you're looking at memory optimized tables. Right,
and we talk about hot pages there. I always, whenever people ask me about this, I always sort of explain this as being, imagine you've got a table of orders and you have an incrementing order ID key, and you've created a clustered index on that key. Well, what that means is all the inserts are going to happen in the last page.
Exactly.
So if you've got lots and lots of client applications trying to insert data at the same time, they're all going to be on the last page. At some point, that page is, we're going to escalate a lock to page level and start blocking any new orders being taken. So those types of structures, which make sense in themselves, can lead to you having pages that are particularly, commonly accessed, and those become your hot pages, and that kind of leads to a lot of blocking. Yeah. So this type of technology is really designed to deal with, you've got an application design that gives you this hot page, that leads you to an awful lot of locking and blocking because you've got lots of concurrency. How do you deal with that?
Yeah, and it's really targeted at massive scale. Yeah. The scenarios that this fixes, it's not that the product doesn't work, it's the fact that you're trying to do so much against these tables that you get these hot pages, and SQL Server will manage concurrency on those pages with latching, which is a lightweight locking mechanism. And because we don't have any of these locking semantics and we don't have latching involved, the throughput that you can get from that is much higher.
Okay, great. So let's look at how we actually create these things then. I see we've got a number 1 in the slide title, so I'm guessing there's multiple steps. So why don't you talk us through it?
Yeah, sure. So the first thing we need to do is to add a file group for memory optimized data. So we've got an alter database here. We're adding a file group that contains memory optimized data. So this is a very specific file group that's going to take file stream data. And in the next statement here, we're going to add a file, specify the file that we're going to add, and it's added to the file group memdata in this example.
And I guess in case you're confused, we're talking about in-memory data. You might be wondering, well, why do we need a file group? It's just purely a semantic of the way that tables are created in SQL Server. Yeah. Tables are associated with file groups, so we have a file group that's effectively there as a placeholder for really the metadata that defines that table, and when we persist, although it's held in memory when we're using it, it's persisted to disk so that it survives restarts of the server. So that's why there's a file group associated with it.
Yeah. So the next slide then is around creating a memory optimized table itself. So we're using the normal create table statement here, but we're also adding a couple of extra commands in here. So we're adding a non-clustered hash index here with a bucket count. Mm-hmm. So this bucket count is the number of hash buckets that we're going to make available for this. And the number of buckets that you should have ideally should be the number of unique values that you'll have in that column. Mm-hmm. But it's flexible enough that you can have non-unique values and it will link those together.
It's perhaps worth just stepping back for a minute before we finish talking about the overall syntax. One of the things that's different about memory optimized tables is the indexing, because indexes, as we know from previous modules in traditional tables, are disk-based themselves. They're pages that are stored on disk, and they may be cached, but fundamentally the index is stored on disk. There are two types of index that we can use with a memory optimized table, and this variant that we've got here is a hash index. What actually happens is that the key or keys that you're the key column or the key columns that you're using for the index, a hash algorithm is applied to them to generate some sort of unique value that you can get from those values. that then determines which location in memory this row is going to be stored. So it's very much a case of we hash the value that's the index key. That identifies effectively a pigeonhole in memory in RAM where we're going to put this row. Now, of course, it's possible that two values will hash to the same value, so they'll end up in the same location in memory. And if that happens, what's then stored in memory is the first value that was put there with a pointer to the second one and a pointer to the third one. So you end up with what's called a linked list structure. And this type of index, a hash index, is very, very efficient if your queries are searching on equality predicates. So if I want to find all of the sales where the customer name is Malcom, I would search for equals Malcom. It's an equality predicate. So it hashes that one value, Malcom, goes and finds the location memory where the Malcom records are stored, and it finds them very quickly. There is an alternative type of index called a range index, which conceptually is very similar to the more traditional SQL Server indexes we know of, that are kind of binary tree type structures. Again, it's in memory, so it's not exactly the same as a traditional sort of clustered or non-clustered index we'd create for a disk-based table. But those are more effective if your queries are likely to search for ranges of values. So find me all the transactions between, November and the following January. That's a range of values you're trying to find, and that's going to be more efficient than trying to calculate all the individual hashes that are possible between those values and find the locations in memory. So we're kind of just showing you the syntax. Hash we've highlighted because it's new. It's you won't have seen that type of index before. It's not the only game in town when it comes to indexing in memory tables. So you need to consider that. Anyway, I've probably diverted us far enough.
No, that's fine. That's fine. If we move the slide on, actually, there's a couple of points there, just reiterating what.
There you go. I've peeked too soon.
What Graeme was mentioning. That's fine.
So let's move on to talk about querying memory optimized tables and try and understand a little bit about that.
Yeah. So first of all, we mentioned in the beginning that you can have a memory optimized table, and that you could write a query that accesses a disk-based table and a memory optimized table as well. And the way that it enables us to do that is through this query interop. So we can combine the two together.
Okay.
And the other way that we can access tables is through native compilation. So this is store procedure converted to C and compiled, where you can access only memory optimized tables. So what's interesting about the native compilation is that when you write a store procedure normally, T-SQL is an interpreted language. So while we have it compiled, it's essentially interpreted. So when we execute the code, it has to line by line execute what you're trying to do, which is fine under a traditional model because we're so dependent on disk-based tables that having an interpreted language to access those tables was an insignificant cost in the wider cost of execution. But now we've got these structures that are memory-based, and they're not just pinned in memory. They're actually memory optimized structures that we can get significant savings, not just by having a table that's optimized to be in memory, but for optimizing these store procedures as well. And when you natively compile a store procedure, it's compiling it into C code and presenting this compiled C code that is far more efficient to execute.
So the path that we've got there, though, if I've got a natively compiled store procedure, it can only query memory optimized tables. I can't use that to query.
That's correct.
Right. Okay.
Yeah. So we can have a normal query can read from both, but a memory optimized store procedure can only access in memory tables.
All right. Perfect.
Should we have a quick look?
Let's have a look.
So let's have a look at memory optimized tables first. What we're going to do here is to create a new database specifically for this. So let's do, let's just keep it simple and do create database mem demo. So now we're going to go into the properties of this new database.
So far it's just a regular database. There's nothing special about it.
Absolutely. I'm going to create a new file group in the memory optimized section down here, you'll notice. And we're going to call that MFG. And now we're going to have a look at creating a new data file. We'll call that let's call it memdemo2. Okay. And we're going to put that, we're going to put it in, so this new file type we have here is file stream data. And because the file group that we've created is memory optimized, it's the only file group that's available for file stream data.
Should point out that there is a technology called FileStream that's about storing files in SQL Server, or at least storing documents in SQL Server, and they're spilled out to the file system. This is potentially confusing here. We're using the same type of file group as you would use for file stream storage. We're not using file stream storage in the sense of that feature. We're just using the same type of file group to store memory optimized data.
Exactly, yeah. So let's create that now. So now what we're going to do is to use this database. We're going to create a table that's optimized for in-memory. We've got this non-clustered hash with the bucket count, so this is exactly what we saw in the slide.
And just again to interject, I detracted earlier on when we moved. I diverted us off when we talked about the syntax. So we didn't really have a chance to talk about this durability flag that's here, this option. And again, it's probably worth mentioning there's two different options. This one here is schema and data. So what we're saying is any data that's inserted into this table or updated will be persisted to disk. So that if the server goes down and comes back up, we don't lose the table. Why would I ever want to have durability just the schema and not the data?
So you can think of a scenario where you don't need to persist the data. So you're looking to have data temporarily that's held in memory, and you may want to have durability on the schema and not the data as well.
So maybe session data, I guess, for a website or a shopping cart that. If the server goes down, okay, we lost the shopping cart, but it wasn't a persisted order or whatever.
Exactly. Exactly. So we've created that now, and what we're going to create for comparison is the same table as a normal disk-based table.
So this is the same structure, but it's a traditional
table. Exactly the same structure, yeah. And then we're just going to insert 500,000 rows into the disk-based table, and just have a look at the timings of that.
And you're doing that within a transaction, so it's going to lock as we do that.
Yeah, exactly. So that took 6 seconds to run. I don't know if you can see in the bottom right-hand side of my screen. And if we just have a look at the contents of that table, we've got 500,000 rows there.
Okay.
So and now we're going to do exactly the same thing into the memory table. And that's taken 5 seconds to run. So I was expecting it to be a bit quicker than that, but it's still better than it was onto the traditional table.
Okay.
So let's have a look. So we've still got 500,000 rows there. Now let's have a look at a delete. So if we delete from the disk-based table, so that's taken a second to do that. And if we delete from the memory table, so we're sub-second on that. So the scale that we're running on this, it's always quite difficult to work out the scale because the laptops get faster and faster and faster.
Sure.
So the performance gains from a demo perspective can be quite small, but hopefully what we've demonstrated here is the interaction we've had and a comparison between a disk-based table and a memory-optimized table.
Right.
And there are performance gains that we had through that process.
And I have seen demos where it's a much more dramatic difference as you scale
Absolutely.
up. As you see, your laptop's clearly a very powerful laptop, so the disk-based table is performing well. Yeah. But I've seen demos where the disk-based subsystem is significantly slower, and the semantics of the locking is significantly slowing things down. So there's a dramatic difference between the time it takes to run those two.
There are a few times with this laptop where I regret the fact that it's got very, very fast SSD storage when I'm demoing the difference between that and the memory.
So what you're saying is if I'm implementing an enterprise system, I should either use in-memory technologies or I should use your laptop.
My laptop.
That's the time. Okay.
And then finally, we've got some memory optimized stable statistics that we can get, pulling this out of this additional DMV that we have for in-memory.
Oh, so I can actually keep track of, because obviously the data is in memory, I want to keep track of, well, what's that doing to my overall memory usage?
Yeah, exactly. So it is quite useful.
Okay. Can I ask you, just before we move on to the next little section, could you bring up the file explorer and let us have a look at the file system? Because I think it's probably worth exploring a little bit about what's being created. So if we're going to where our SQL Server databases are stored.
It's probably...
If it's 64, but it'll be in there.
Yeah.
Yep.
Take a guess.
Nope. It's not there.
The other one.
So into the data folder, there's an XTP folder. Let's have a look in there. And into 9. And you see a bunch of files here that have been generated. Now, these have been generated by SQL Server, and anybody who's done any software development will recognize some of these that are object files and PDB files and out files, which are used as part of the compilation process to ultimately produce that DLL file, which is the DLL representing our table. And I guess what's really interesting is right at the top of that list, there's a C file. So if you can go ahead and double-click that guy, and let's open that up in Notepad. Here's the actual C source code that SQL Server has generated to represent that table. So there's a struct in here that is used to implement that table, which will have all the public fields that are the columns in the table. So you can actually drill right under the covers and see what's going on when SQL Server actually generates these in-memory tables.
That's really good.
So, and we talked about our tables. One of the things we didn't see in the demo there that we mentioned earlier on was natively compiled stored procedures. So let's have a little chat about those.
So we've mentioned this before when we were talking about this query interop where you could write normal T-SQL and you could read from a disk-based table and a memory optimized table, and we've also talked about this idea of natively compiled store procedures. And again, just to reiterate this point, is a traditional store procedure. T-SQL is an interpreted language, which was never a problem when we're working with disk-based tables. But if we're working with things in RAM, which is really, really fast I/O, we can get a lot of performance gains if we can compile these store procedures into a C structs like we've seen with the tables as well.
Okay, so I can see some differences in the syntax there compared to creating a regular stored procedure. The obvious one is the with native compilation.
Yeah.
We've got schema binding, which we saw before when we talked about views. The idea is if anything underneath this, anything this thing depends on changes, well, actually don't allow anything that this thing depends on to change. We've got the execution context, so who is this going to run as? And in this case, it's going to run as whoever the owner of the stored procedure is. And then I've got something that looks like a transaction, but the syntax is different from what we've seen. It's begin atomic with, and then I specify an isolation level for this, and it so happens you also have to specify a language, which is part of the requirement. So I guess it's worth being aware of that. The reason this is different from the semantics you've seen when creating transactions in Transact SQL for ordinary stored procedures is again due to the fact that it's stored in memory. So the underlying semantics as to how this is done is different, and this syntax is baked into the DLL that gets compiled. But the effects are the same. Effectively, we'll end up with this being a transaction that uses snapshot level, isolation level. Yeah. Okay, so we'll hop back to the demo machine.
Should we round up with a demo of these compile store procedures? Okay, so we're going to use this same database again, just to make sure we're in there. So this time, instead of running this code to insert these 500,000 rows, we're going to create a natively compiled store procedure called insert data. And we're going to execute that store procedure. So can you remember how long it took to insert
into the memory optimized table? When we just ran the transit SQL, it took 5 seconds.
It was 5 seconds and 6 seconds for the disk-based table.
One,
So let's see how quickly this is. So less than a second.
Wow, it's instantaneous. Yeah.
So there's a massive difference. So while we had a performance gain of switching from disk-based table to memory optimized, the real massive gain we've got there is by switching to a natively compiled store procedures to do the same operation.
Fantastic, brilliant. Okay. So we covered a number of things in that module. We talked about the buffer pool extension, which was not an in-memory technology per se, but a way of taking data that's normally cached in RAM memory and moving that out, spooling that out onto a fast disk, a fast storage device, so that we're making more use of our fast solid-state storage, and we're able to maximize the way that we're using our RAM and get better use from fast storage. We talked about column store indexes, both the non-clustered variety, which have been around since SQL Server 2012, all those years ago, 2012, and also the clustered column store indexes in 2014, which, if you remember, are updatable, whereas the non-clustered ones make the table non-updatable. And then finally, we talked about InMemory OLTP, or Hackathon as the code name was, where we talked about memory optimized tables and those memory optimized store procedures that we've just seen, where you can see some significant performance benefits in particular workload types.
Absolutely.
So I hope you've enjoyed this module. Again, the usual rules apply. Go off and have a look in SQL Server books online, research this stuff, play around with it for yourself, make sure you're comfortable with that technology and with these different techniques, and then come back and join us for the final module in this course, where we'll look at optimizing and troubleshooting performance. So I look forward to you joining us then. Well, we made it. We're at module 6. We've made it through to the final module of the course. I hope you're all still with us out there. We're going to finish off the course with a look at optimizing and troubleshooting queries. We've talked a lot about different techniques for implementing a database throughout the course. And at the end of the day, databases are about accessing data, and for a lot of users using applications, the area they're going to get concerned about is the performance when they're doing that, and when things go wrong, how do we make sure we optimize that performance? So Christian, I'm going to ask you to tell us what we're going to cover in terms of optimizing and troubleshooting.
Great, thanks, Graeme. So for this module, what I wanted to really talk about is a few things really around kind of optimizing and troubleshooting tips. So the first thing that I wanted to talk about is SQL Server weights and the concepts and architecture that supports the idea of a weight. And then we'll talk through a specific scenario that from within my role, we see a lot of these kinds of problems around joining too many tables, and I'll show you why that's a bad idea in terms of how the optimizer works. And then finally, we'll have a slide at the end where we can have a discussion around some other performance tuning tips that have maybe been sprinkled around these 6 modules, that we can consolidate those and close off the course.
Good enough. Okay, let's start with weights.
Great. So if we think about the way SQL Server works, first of all, and we'll walk through this diagram. So when you connect to SQL Server, you'll connect in the context of a session. and then which we would track with a session ID or a SPID in old money if you've been around SQL Server for a while. And then when you execute something, so you execute a piece of code, SQL Server will generate a task, which is this kind of internal structure that's used to provide a context for the execution of what you're trying to use. So we have this task concept. Now this a task will then be assigned a worker thread. So a worker thread we don't actually have on this diagram. So we have a session, a task, and we'll have a worker thread that is assigned to execute the tasks. So when we talk about things running, the only thing that actually runs is a thread, is a worker thread. It's just we kind of abstract it all the way up to an application or a user or whatever. Okay. So we have this session, task, and worker thread. So the worker thread will be assigned to what we call a scheduler. Okay. And the scheduler's job is to schedule time for workers to execute on a processor. So by that I mean a logical CPU as we have in this diagram. So you may have hyper-threading, you may have virtual CPUs. SQL Server doesn't care about what your kind of process architecture is underneath. When SQL Server starts, it will look at the number of CPUs that it sees when it starts, and it will generate one scheduler per CPU.
Okay.
Okay, so and we call this scheduler, scheduling time for threads on a CPU, we call this a cooperative scheduling model. So this is SQL Server's scheduling model of scheduling threads on CPUs.
So I guess when we're talking about multitasking is the term people use when they talk about how computers do their work. Of course, what's happening is you've got a query that might take a long time to run, and you've got other things that are running as well, and we're effectively time slicing, where we're sharing that CPU across lots of things that are happening.
Exactly.
And the thread goes on and off and on and off as it...
Exactly. Yeah. So this is where fundamentally a CPU can only ever do one thing at any one time, and it gives the illusion of multitasking because it's switching between these threads very, very fast. We call that switching context switches. Okay. So if you ever looked in Perfmon and you have a look at context switches a second, so this is what it's referring to, flicking between worker threads on a CPU. Right. So if you see a high number of context switches a second, it's an indication that there's a large number of workloads trying to compete for time on the CPU.
For limited CPU resources.
Yeah, okay. Exactly. So, so we call SQL Server's scheduling mechanism a cooperative scheduler because while this thread, the thread that's running your piece of code, is running on the CPU, if it doesn't need CPU time anymore in terms of, in order for me to continue processing, I need to get some data off disk. It will voluntarily yield its time on the processor to let somebody else have a go. So it cooperates with other threads in order to provide a more efficient execution model.
Okay, makes sense.
Okay. If we just go back to that slide and we'll talk about the, as opposed to Windows, which has a preemptive scheduling model. So Windows is a general purpose operating system from my desktop to a powerful server. It's written specifically for multiple programming languages, multiple applications, multiple uses, and there's nothing to optimize Windows on my laptop over Windows Server specifically for any particular application. So this is what we call a preemptive scheduler. And a preemptive scheduler model, you get a time slice in order to do your execution. And whether it's convenient or efficient for you to stop, you'll get kicked off to let somebody else
Windows
have a go.
turfs you off to let somebody else use the processor.
Exactly. So, and this is where in the SQL Server 6.5 time frame, the SQL Server team created this cooperative scheduling model in order to control the Windows scheduler in a more cooperative manner.
Okay.
And this is all leading on to something important, I do promise. It's not just an exercise in how things work.
Okay.
So this leads us towards this SQL Server weights architecture. So when we talk about threads, so threads can be, for the purposes of this kind of understanding weights, we talk about threads being in one of three states. So the first is a running state. So this example, we have a thread running under the context of session ID 55 on scheduler 1. Mm-hmm. So on scheduler 1, we're assigned to a processor. Okay. And we can only have one thing running on a processor at once. Therefore, we can only have one thread on scheduler 1 in a status of running, and that's the thread that is executing on the processor.
Okay.
Make sense?
Yeah, absolutely, yeah.
So if you're not running, then chances are you're suspended.
Okay.
So, and when you're suspended, so this is an example of where, because we're running in a cooperative scheduler, I still need to run, but I need to get some data first. So rather than me holding up the CPU, I'm going to voluntarily yield. I'm going to switch my state to suspended, and I'm going to store information about what I'm waiting for. So anything that's in this suspended state is what we call a SQL Server wait.
Right, okay, that makes sense.
Yep. And the third state that I wanted to talk about is this runnable state. So we're running in this cycle of I'm running, I voluntarily yield while I wait for something from disk, for example. And then I get that information back, and I need to get back onto the CPU. So then I'll join the runnable queue. So I'm queuing up to get back onto the running state again.
Okay, so I've been on the merry-go-round, I got off to give somebody else a go, and now I rejoin the queue to get back on.
Exactly. So time spent, anything in the suspended state is what we call a SQL Server wait, okay. And anything that is runnable is what we call a signal wait. So a signal wait is a way to track CPU pressure effectively, because anything that's runnable is effectively just waiting to get onto the CPU. So if we could have a look at signal waits, it would be an indication of CPU pressure.
Okay.
But the main area that I wanted to get across with this is this concept of a SQL Server wait. So we have 4 sessions in there that are running tasks. We've got a couple of wait types in there, which we'll talk about on the next slide, actually, in terms of useful wait types.
Okay.
So when we're voluntarily yielding, there will be places in the code that will log, effectively, what that thread is waiting for. And if we can track what threads are waiting for and aggregate those, we can essentially have a look at what the bottlenecks are in the system.
Right, okay.
So some of these useful wait types, so page IO latch, for example, is a latch on a page in memory. So if you wanted to read data from a table, everything that you do within SQL Server has to go into memory. So you do a select star from table name. That data has to go in memory before it gets sent out to you. Mm-hmm. So what SQL Server will do is to put a latch on a page in memory in order to, so it's basically saying, I'm going to use this in a minute, so nobody else use it, while I go and get the data to put into it. Okay?
Okay.
So this wait is, I've taken a page IO latch and I'm waiting for it to be filled. So a page IO latch is a pure wait on reading data from disk to put into memory. So it's an indication of slow IO. If you've got a page IO latch wait.
Okay.
So the second one we have on there is a CX packet. So this is a synchronization packet. So this indicates that we have parallelism running on the system. Okay. It doesn't necessarily indicate a problem, but it's the synchronization between parallel threads. So you'll always get CX packet waits where you have parallelism.
And by parallelism, we mean there's multiple processors or multiple virtual processors.
Yeah, so we've got multiple processors. As we had in the diagram, we had 4 processors. Yeah. And if SQL Server determines that what you're trying to do is expensive enough to overcome the overhead of breaking it into parts and running it across multiple processors, it will run that query in parallel, and that's what we mean by parallelism.
Okay.
So CX packet, rather than indicating a problem, indicates that we have expensive queries.
And we're trying to synchronize them across multiple processors?
No, it's actually, so if we have 4 we're running in parallel across 4 processors.
Yeah.
So that's 4 threads.
Right.
So we have each one of these threads will have a packet of work to do. So I'll give you each 2,500 rows to process.
Right.
So this guy finishes his first. So then he's waiting on CX packets because he's waiting for the other guys to finish. Okay. So what you end up with is several threads that are finished, and you've got one that ends up having to do more work than the others, and that's what you're waiting for.
I see. Okay.
Anyway, the short story for CX packet wait is that it indicates parallelism, which indicates expensive queries, and if you're running on an OLTP system, you're not really expecting big expensive queries to be there. So it's an indication that you would go and investigate and find these big expensive queries and see if they're expensive because they haven't been written properly, or that they need to be expensive in order to achieve the business logic.
Okay.
So the next one on there is write log. So write log wait is a wait to write to the transaction log. So this is a kind of a high level indicator of transaction log write performance. So there's a good indicator there. So LCK, do you remember we saw this earlier on?
We looked at locking, yes.
We did. We looked at locking. So one of the nice things about tracking and looking at wait types is that it's not just around resource utilization and resource weights, but it also involves locking as well. So what we saw during the demo earlier was an LCK on a shared lock. So we were waiting to get an exclusive lock that was being blocked by a shared. Mm-hmm. And we also have these preemptive wait types as well, which were new with 2008 actually. Mm-hmm. And preemptive, you remember where I mentioned preemptive earlier in this session?
So Windows preemptive.
So Windows has a preemptive scheduler. So whenever you see a wait type that is prefixed with preemptive, it means that SQL Server is waiting for Windows to return something.
Okay.
So a good example of where we've had that. We had a customer that had problems. Nobody could log into SQL Server, and or the application couldn't log into SQL Server. And we found that we could log in using a SQL Server account, but not with domain accounts. And what we found is when we had a look at the wait types, everybody was waiting on preemptive authentication ops wait type. And basically this was an indication that SQL Server was waiting to enumerate Windows groups from a domain controller, and we found that the domain controller was broken. Right. So by looking at SQL Server, we could tell the customer that they had a problem with their domain controller, because we had this new kind of preemptive wait types. And another one as well for anything that happens in the file system will also have a preemptive wait type as well. So if you're doing, a SQL Server needs to do an auto-grow event, or you're creating a big file or anything like that, we'll also have a preemptive wait type for file operations. So you can see SQL Server, your query is not running, but you have a look at the wait types and you find it's actually trying to auto-grow a file on disk.
And we're waiting for Windows to finish
doing that. So it's really, I'm quite passionate about using wait types as a troubleshooting tool, because everything from a slow file system to a broken domain controller to locking problems, you can see within this kind of single view, which is really quite powerful.
Okay. So if I want to view these weights, up till now we've seen lots of different dynamic management views for viewing different things, and we actually saw one of these to look at weights in one of the previous demos. So
we did, yeah.
So start with those.
So the first one is really sys.dm exec requests, and you can think of this as I like to think of it as a replacement for SP_who that we would have used in previous versions, a store procedure to return who's doing what. So dm exec requests provides wait information at the session level. So remember we talked about sessions and tasks. You execute something and it spawns a task to run within this context.
Okay.
So if you think about an example of a parallel query, will spawn multiple tasks. But if you're having a look at dm exec requests, this works at the session level only. So you're not going to see the wait types for any more than one task that's sitting at that level.
Okay.
Does that make sense?
It does.
So it does provide a bit of information there, but what we're really interested in is working at this task level. And this is where we would use DMOS waiting tasks to find out exactly who's currently waiting for something.
Okay.
So I've said that this is it's very accurate in here because it's a live view on who's waiting for what at the time that you select from this DMV. And because of the nature of SQL Server and the way things execute, somebody is always waiting for something.
Sure.
So every time you view this query, you get this massive result set that flexes like this. So it's really useful for a live problem.
Right.
You get a call, everything's running slowly, what's happening? I would go and have a look in this DMV to see somebody's probably waiting for something, and it would have it on there.
Okay.
But if you've got lots and lots of users that are waiting for a very short time period, so it's not really noticeable, but over time that would have a cumulative effect on the overall performance. We would look at this final one here, which is DMOS wait stats. So wait stats stores, instead of a row for anything that's waiting for something, it's a row for every possible wait type, and then it has aggregated statistics of how many tasks have ever waited for that wait type, what is the longest time that anyone's waited for that wait type, things like that.
So it's historical data that lets me see, hey, I seem to have an awful lot of preemptive waits, for example.
Yeah,
maybe there's something in the Windows subsystem I need to look at.
And this is one of the first things that I would have a look at. If I was having a look at, I sat down in front of a SQL Server that's got performance problems, I'm really quite interested in what historically, since the last restart, have things waited for. And quite often you'll see obvious things will bubble up to the top, like preemptive or disk problems or locking problems, and you can get a good indication of why things are running slowly in the environment.
Okay, great. So I'm guessing you're going to show us some of that.
Yeah, let's have a quick look. So what I wanted to do here is we'll switch back to this people database that we used towards the beginning of the day. We'll have a look at these DMVs first. So we'll do DM exec requests. So this is one row for any executing tasks, effectively. So there's lots of background threads. I'm going to modify these to do where session ID is greater than 50. So this is going to show me all of the user-generated sessions. So just to caveat that, anything greater than 50 will be a user session will always be greater than 50, but there are circumstances in which system-generated sessions there's more than 50, so it will spill over.
Okay.
Does that make sense? So if I'm just looking for user sessions in general, I would use this kind of filter. So I've got two sessions here. I've got session ID 52, which is where I am. Let's just run that select statement. Let me take a copy of that so we can use it. If I have a look at DMOS waiting tasks, do you remember I mentioned this kind of transient view? So there are lots of things.
So this is what's currently going
waiting
on.
for stuff, yeah. But a lot of these things are benign waits. They're system threads waiting for something to happen. So anything that has sleep or poll or wake up, we would tend to ignore.
It's in the background.
It's waiting for something to happen. It's not causing a problem.
Okay.
But again, I would kind of filter that on session ID equals 50. So I've got 53 is waiting on a trace write, which is probably the trace that we were running earlier in the day is still running in the background. Yeah.
Okay.
So if we have a look at finally this DMOS wait stats.
That's all in this episode. I hope this tutorial was helpful. In the next episode, we will be back with another episode of another interesting course. Is your mind ringing with questions, queries or doubt? Do you wish to learn more? Then visit our website www.millionlights.org and post your questions on our forum. We will be really happy to clear all your doubts. If you missed anything or want to rewatch it, you can download it from our website or can watch online as well. You can also participate in our webinars, discussion with the subject expert, as well as get Microsoft certification on various courses through our website. You can also find us on Facebook by the name Millionlights and also on Twitter. For more such interesting tutorials on coding, app development, programming, and building rich UIs, keep watching Microsoft Hour of Code brought to you by Millionlights. Thank you.